Hey everyone, I'm Kelly of metric number 157371. Today I'm going to talk about the mini project of ZCE 111 entitled the Stefan-Boltzmann constant. First of all, let me give you a brief introduction about Stefan-Boltzmann constant. Stefan-Boltzmann law states that the total radiant heat power emitted from a surface is proportional to the fourth power of its absolute temperature in Kelvin, and this can be represented by an equation known as E equals to sigma times T to the power of 4, where E is the radiant heat energy emitted from a unit area in 1 second, and T is the absolute temperature in kelvins, where sigma is the Stefan-Boltzmann constant. The Stefan-Boltzmann constant has a value of 5.67 times 10 to the power of negative 8 watt per meter square per Kelvin to the power of 4. This law only applies to only black body, theoretical surface that absorb all incident heat radiation. And in this assignment, we are to integrate the thermal energy in order to obtain the total energy per unit area radiated by a black body, and also to write a code in order to determine the value of Stefan-Boltzmann constant and compare it with the theoretical value to see their percentage of discrepancy. Next, I'm going to talk about the procedure in this mini project. For the very first part, as given by the question, a black body of unit area radius electromagnetically and amount of thermal energy per second equals to I omega d omega, where I omega equals to h over 4 pi square c square times omega to the power of 3 divided by e to the power of h omega divided by k times t minus 1. We are to use the method of integration to prove that the work done in this thermal radiation is equals to k to the power of 4 t to the power of 4 divided by 4 pi square c square h to the power of 3 times the integration of x cubed divided by e to the power of x minus 1 integration from 0 to infinity. Next, we need to evaluate the value of the Stefan-Boltzmann constant using Python. First, we need to import NumPy library and also scipy.integrate to the code. Next, we need to state all the values needed. For the fourth step, we need to define the function of integral, and for this question, the integral is given by x cubed over ex minus 1. And as well as its lower and also upper limit. The lower limit will be 0 and the upper limit will be infinity. For the fifth one, we need to evaluate the value of sigma by multiplying the value of the integral generated with k to the power of 4 divided by 4 pi square c square h to the power of 3. The value of the sigma can be generated, and for this case, we need to fix the value of the sigma to 3 significant figures. For the last step, we compare the value of the calculated Stefan-Boltzmann constant with the theoretical value. Next, for part 3 is the results part. The Planck theory of thermal radiation tells us that in the angular frequency interval omega to omega plus d omega, a black body of unit area radius electromagnetically and amount of thermal energy per second equals to I omega d omega, where the equation is given as shown in this slide. Here h is the Planck constant over 2 pi, where c is the speed of light and k is the Boltzmann constant. We need to show that the total energy per unit area radiated by a black body is as shown down there. So given that I omega equals to h over 4 pi square c square times omega 3 divided by e h omega divided by kt minus 1. So by taking x equals to h omega divided by kt and perform differentiation of dx d omega, we can get dx d omega equals to h over kt. So d omega will be kt over h times dx, or can be known as omega x times dx. So we know that work done equals to I omega and perform the integration from 0 to infinity. So by substituting the content of I omega, we can perform the integration as shown in this diagram, and by replacing d omega with omega over x times dx, and also by replacing h omega times over k times t with e to the power of x, and we can perform the integration as shown in this figure, and eventually we can get the final answer k to the power 4 times t to the power 4 divided by 4 pi square c square h cubed times the integral of x cubed divided by ex minus 1 integration from 0 to infinity. So the final answer for this part is being shown and being in all is proven. For part B, write a program to evaluate the integral in this expression. Explain what method you use and how accurate you think your answer is. First and foremost, import numpy as np and import size5.integrate as si. Next, we need to state all the constants we need to evaluate the value of the Stefan-Boltzmann constant. For integral in this part, integral is defined as x cubed divided by e to the power of x minus 1. This is the function of the integral. So a equals to 0, b equals to np dot infinity, which is the lower and upper limit for this integral. Result equals to psi is equal to size5 dot integrate dot quad bracket I comma a comma b. For this part, the result will return to two values. For the first value is the value of this integral, and the second value is the error of estimation for this integral. Next, we need to print the result for this integral. For the first value of integral is written as result square bracket in 0. This is the value of the integral. Result bracket in 1 is the area for this integral. So for the sigma, in order to evaluate the value of the Stefan-Boltzmann constant, we need to times the value of the integral, which is given by r, and we have performed this calculation at the above part. So what we need to do is we need to times the constant part, which is equals to k to the power 4 divided by 4 pi square c square h to the power of 3. Next, for the print part, we need to print and also format the value of the Stefan-Boltzmann constant to 3 significant figures, which is requested by the question. So as you can see here, the result has a value of the integral is 7, and the error for the integral part is equals to 2.02 times 10 to the power of negative 8. And the value of the Stefan-Boltzmann constant evaluated here is 6.10 times 10 to the power of negative 8. Part C. Even before Planck gave his theory of thermal radiation around the turn of the 200th century, it was known that the total energy W given off by a black body per unit area per second followed Stefan's law, which is given by W equals to sigma times T to the power of 4, where sigma is the Stefan-Boltzmann constant in SI unit to 3 significant figures. Check your result against the known value, which you can find in books or online. You should get good agreement. So as you can see the table here, the calculated value is 6.10 times 10 to the power of negative 8 watt per meter square per Kelvin to the power of 4, whereas the theoretical value is 5.67 times 10 to the power of negative 8 watt per meter square per Kelvin to the power of 4. So the difference between calculated value and theoretical value is 0.43 times 10 to the power of negative 8 watt per meter square per Kelvin to the power of 4. The percentage of discrepancy for this case is 7.58%, where it can show that the calculated value forms a good agreement with the theoretical value. So now we have come to the last part for this mini project, which is the discussion part. At the end of this project, we can conclude that from the Planck theory of thermal radiation, the total energy per unit area radiated by a black body can be derived, which is the first objective for this mini project. Next, we need to evaluate the value of the Stefan-Boltzmann constant by using the value of the integral. And for this case, we can achieve easily by using the method of size pi dot integrate. And as you can see from the previous part, the calculated value forms a good agreement with the theoretical value. So I think that's all for this mini project. And thank you for lending me your eyes and ears. Thank you.